talk on cryptography. Let me start this talk by giving some terminology. The first thing I want to speak about is about information. So by information, I mean any kind of data, for example, your identity, the number of your credit card, the messages you want to exchange, the files you want to send you have on your computer, and the things like that. By cryptography, I mean any kind of protocol that we may set up to protect information. And in general, when we speak about cryptography, to illustrate our purpose, we consider some characters and kind of scenario that I will be presenting to you. The first character I want to present is called A or Alice. So Alice may be a person like you and me, or maybe it's a bank, or maybe it's a company, or a site on internet, or an institution, or anything of that kind. The second character is called B or Bob. The same thing for Bob, maybe a person or a bank or anything like that. And these two persons, they want to exchange information, or these two institutions or entities, they want to exchange information. The point is that the zone through which they want to exchange is not secure, a secure zone. By not being a secure zone, I mean that there may be a person here called Eve, going for eavesdropper, that may intercept these exchanges. For example, if Alice wants to send a message to Bob, Eve may intercept the message and read the message, while she is not allowed to. We don't want to be the case. So this person is called an adversary. Sometimes this is a passive adversary. All she does is just looking at the messages and try to intercept and read the messages. Sometimes she can be active. For example, she can contact Bob and say, "Hey Bob, I am Alice." So she may pretend to be Alice, or maybe she intercepts some message from Alice, keeps the message and sends another message to Bob instead of Alice. So we want to prevent these kind of things. To prevent these kind of things, we need to make the exchanges between Alice and Bob secure. By which I mean, if Alice wants to send a message to Bob, she has to encrypt her message before sending it to Bob. This way, even if Eve intercepts the message, she doesn't understand what is written in the message. And we have to set up other protocols to make it sure that Eve cannot pretend to be Alice and contact Bob and the things like this. Now, in short, cryptography sets up protocols to achieve or to provide the following things. The first thing is confidentiality, which means that Alice can send messages to Bob and no one else than Bob can read the message. Second thing is digital signature, by which I mean Alice signs her messages and Bob now is sure that the message is coming from Alice. And also, Alice cannot deny that she has sent some message that she has signed, because it may happen that Alice orders something to her bank to put some money from one account to the other, and she signs the message, and after a few days maybe she denies it. She says it was not me that ordered. But if she signed her message, she cannot deny it afterwards. That's an important point, and it's called the non-repudiation. One other thing that cryptography achieves is authentication. We may set up some protocols to make sure that no one can pretend to be Alice. And also, we may have some protocols for message authentication, for secret sharing, electronic voting, and so many other things that we can achieve with cryptography. Now, the simplest cipher or crypto system that we know goes back to about 2,000 years ago. It is called Caesar's cipher or Caesar's crypto system. In this crypto system, you have the alphabet from A to Z, and the way you encrypt messages is that you push any character or any letter 3 ranks forward. So to encrypt the letter A, you write D instead of A. You push A 3 ranks forward, and so on. So for example, if you want in your message you have the letter X, X will be pushed 3 ranks forward. Well, when you push it 2 ranks, you are here, but 3 ranks, you come back to A. So the encryption of X will be A. The encryption of Y will be B. So it's somehow cyclic. In any case, if you have the message, say, come, which is called the plain text, and you want to encrypt it, the letter C of come will go to F, as I said, 3 ranks further. So C becomes F. O becomes R. M will be encrypted by P, and E will be encrypted by H. This message FRPS is called the ciphertext. So Alice, if Alice wants to send the message come to Bob, she encrypts her message, which becomes FRPH. She sends this encrypted message to Bob, and of course Bob has to do the other way around to refine the plain text which was come. So Bob pushes every letter 3 ranks back. So F becomes C, R becomes O, and etc. And Bob can get back the plain text which was come. Now, I want to put some mathematics into this crypto system. Not that this crypto system is secure. This crypto system is far from being secure. But the mathematics I want to put into it will be very useful everywhere in cryptography. So I will be speaking about modular computation now, some basic mathematics. I take the real line, which I glue to a circle like this at the point 0 here. Then I wrap around the real line around the circle such that this one point here comes to the bottom of the circle. I wrap around so this positive part of real line, 1 comes here. I wrap it around the circle, 1 comes here, 2 goes to the same point as 0, and so on. 3 comes here, 4 comes here, and so on. For the negative part of the real line, The other way I wrap around, so this -1 comes here, and then you wrap around, -2 comes to 0. So this way you get two classes. The even integers, they are just on this point, and the other integers, the odd integers, they are at the bottom of this circle. In this way, we obtain a set that I denote by z over 2z. The elements are two classes, the even integers and the odd integers. Every element in a class is called a representative of the class, and you may note that if I divide any integer of this class by 2, the remainder is 0, and if I divide any element of this other class by 2, the remainder is 1. So 0 and 1 are the privileged representatives of these two classes. That's why I write this set as 0 bar and 1 bar. The bar is just to say that these are classes and not just one element. Okay, so far we got a set, but I want to say that you already knew about this, because if you look at a clock, you say that you have 1, 2 to 12. If you imagine that you wrap around this circle the real line, you have 1, 2 to 12. 12 is coming back to 0. Here you have 13, 14, and so on. And if I may say, the set of this clock is the set z over 12z. And the elements or the classes are the class of 0, 1 to 11. Now, so far, for any n, for any integer n, one can consider the set z over nz, consisting of n classes. And I want to define addition, subtraction, multiplication, and eventually, if it's possible, to define division on these sets. So fix some n, some integer n, consider the set z over nz. Just a remark here. If you get two integers inside the same class, you see that x prime in the same class, x minus x prime is some multiple of n. This is a simple fact, which is very useful afterwards. So for two classes, x bar and y bar, I want to define what is x bar plus y bar. So I say that I take some representative of this class, say x, another representative for this class, say y. I sum up x and y. It gives me the element x plus y. I take the class of x plus y. This will be the definition of addition of classes. So I have to say that it's well defined, which means that if someone else take another representative here, say x prime, another representative here, say y prime, and x prime plus y prime is some element, I have to say that the class of x plus y and x prime plus y prime is the same class. This is easy to do using this fact here. Okay, the same way I can define subtraction, multiplication of classes, but regarding the division, we cannot divide by any class. So one can divide by a class x bar of z over nz if and only if a representative x of this class is co-prime to n. Being co-prime to n which, means that there is no common factor between x and n. In this case, we can write 1 over x bar or x bar to the minus 1, which is the inverse of x bar, the class x bar. In short, all I have explained till now is that there is a ring structure on the set Z over nz. I give some examples of this modular computation. For example, if I consider Z over 26Z, you may imagine over the circle 0, 1 to 26. 26 is the same as 0. So if I want to compute 19 plus 16, which makes 35, as I am computing modulo 26, I divide this by 26. It gives 1 times 26 plus 9. 26 is the same thing as 0, so this term disappears, and it gives me just 9. And 9 is the remainder of the division of 35 by 26. So in short, 19 plus 16 is just equal to 9 modulo 26. Or if you have 3 times 23, which makes 69, we divide it by 26. It gives 2 times 26 plus 17. 26 is 0, so all this equal to 17 modulo 26. The same thing if I want to compute the inverse of 3. 3 is co-prime to 26, so the inverse of 3 exists, modulo 23. And one can compute in general using the extended Euclidean algorithm the inverse of any element. I'm not explaining this algorithm in detail, but one can compute the inverse of 3 modulo 26. In fact, the inverse of 3 modulo 26 is 9. Why is that? Because 3 times 9 is 27, which is 1 times 26 plus 1, and 26 is 0, so the result is 1. So 3 times 9 is 1 modulo 26. And so 3 and 9 are the inverses of one another. So with this basic mathematics, I come back to Caesar's cipher, and I want to explain it mathematically. So we had the alphabet from A to Z. Because I want to put mathematics into it, I translate these letters by numbers. So I say A is 0, B is 1, and Z is 25. And the crypto system was the following, that we pushed the letters 3 ranks further. So A went to D. So A is 0, which goes to 0 plus 3, which is D. B is 1, goes to 1 plus 3, which is E, and so on. You see that W here goes, W is 22, goes to 22 plus 3, which is Z. X, which is 23, goes to 26. But we said that x comes back to A, and A is 0. So I want 26 to be equal to 0. If I want 26 equal to 0, it means that these numbers 0 to 25 that I written here, I want this to be equal to be in the set z over 26z, such that 26 is the same as 0. So my alphabet is identified by the set z over 26z. And the Caesar cipher is simply the function going from z over 26z to itself, bringing any alpha to alpha plus 3. This is the encryption function. And to decrypt, of course, decryption is the inverse of this function, and the inverse of this function is just any beta here goes to beta minus 3. The key of this crypto system is 3. The decryption key is minus 3. Now, you may say that it is so complicated when I put mathematics in this simple ciphertext cipher, which was Caesar cipher, which was very easy at the beginning. Well, the point is that when you put mathematics in cryptography and even in any other area, it allows you to go really far away. And it's the same thing with cryptography. I give an example how you can go far away with mathematics. So to encrypt the message COM, we can take blocks of 2 letters. You can cut this message COM in block of 2 letters, CO and ME. I'm speaking here a little bit about linear algebra. So this block of letters CO, I can consider it as if it was a vector 2 and 14. C is 2, O is 14. And ME is the vector 12, 4. M is 12, E is 4. You may take an invertible matrix of size 2, 2 by 2 matrix, which you take as to be the encryption key. The coefficients of this matrix must be in Z over 26Z. So this matrix, which is just a table, for those who don't know what a matrix is, it's just a table. The elements here, 3, 5, 4, 7, are the elements of Z over 26Z. Now, how to use this matrix to encrypt messages? I take this matrix, which is the encryption key. I merge COM. So these 2 examples that I just gave are the examples of symmetric cryptography. By symmetric cryptography, I mean the kind of cryptography in which whenever you have the secret key of encryption or the encryption key, we can deduce immediately the decryption key from it. Now, there are 2 problems with symmetric cryptography. The first problem with symmetric cryptography is that before Alice and Bob start to exchange anything, they need to share a secret key to use for their system. Now, they have maybe they have to meet in person and share a secret key, and it is a problem because if Alice and Bob are banks or are some institutions, they have to meet each other, so it may be not so easy. The other problem with symmetric cryptography is that Alice may want to interact with so many people, not just Bob. So if Alice wants to exchange messages with n people, she needs to have n secret keys, share a key with everyone, and then she has to keep all these secret keys on her computer and protect all these secret keys, which may be a problem. So the question arises, which is the following. Is it possible that Alice has just one public key that she can publish in a telephone book or something like that, or on internet, and everyone can use this public key of Alice to send to Alice messages, encrypted messages, that only Alice is able to decrypt? And the answer of this question is yes, it is possible to have something like that, and this is called asymmetric cryptography or public key cryptography. Asymmetric means that there is a public key, and of course there might be a secret key of Alice that Alice knows about, and that she uses for decrypting messages. So there is a public key, there is a secret key. The first example of public key cryptography was proposed by Rivest, Shamir, and Adelman, and it is called RSA. It is based on say there are two ingredients on which this system is based. The first ingredient is that if I give you two prime numbers and I ask you to multiply them, it's an easy task for you. You say that the result is 91. But instead, if I give you, say, if I give you the number 143 and I ask you to factorize this, you may need some or a few seconds to give me the answer. And the answer is, in fact, 11 times 13. So in general, factorization is much more difficult than multiplication. And in fact, if n is a very big integer, the factorization of n might be very, very difficult. So this is the first ingredient of RSA. The second ingredient of RSA is the Euler Fee Function. Now, for any integer n, phi of n is the number of integers less than n and co-prime to n. So for example, if I consider the integer 6, I want to compute phi of 6, I can list the integers less than 6, which are 1, 2, 3, 4, 5. Between these integers, 2, 3, and 4 have common factors with 6, so they are not co-prime to 6. All remains here is just the integers 1 and 5, which are co-prime to 6. So phi of 6 is just 2. So you may wonder if computing phi of an integer is if I have to do this thing, list all integers before say less than some n, and see if they are co-prime or not to n, to compute phi to n, phi of n, it will be a very difficult task to do. In fact, the difficulty of computing phi of some integer n is the same as the difficulty of factoring. If you know how to factor n, it's very easy to compute phi of n. But if you don't know how to factor n, it is as difficult as the factorization of n. And why is that? The point is that this function phi is multiplicative. So if you take two prime numbers p and q, we know that phi of p times q is just phi of p times phi of q. So phi is multiplicative, and it's something that is known. Now, phi of p is very simple to compute because all integers less than p are co-prime to p. So phi of p is just p minus 1. Phi of q is q minus 1. So this way, it's very easy to compute phi of anything if you know the factorization of the integer. So for example, phi of 15. 15 is 3 times 5. Phi of 15 is phi of 3 times phi of 5, which is equal to 3 minus 1 times 5 minus 1, which gives us 8. So phi of 15 is 8. In fact, in this case, I can list all integers less than 15 and find out all integers who are co-prime to 15, which are 1, 2, 4, 7, 8, 11, 13, and 14. Now, we may use a general fact coming from group theory, which assures that all these integers that I listed here, 1, 2, 4 till 14 here, if I put this integer to the power of phi of 15, which is 8, I get, every time I get 1. So 1 to 8, 1 to the power of 8 is equal to 1 mod 15. 2 to the 8 is the same thing. 4 to the 8 is the same thing. And 14 to the 8 is equal to 1 mod 15. This fact will be needed in general later. Now I will be explaining RSA in general. So Alice takes two big numbers p and q, which she keeps secret. She then computes n equal to p times q, which she keeps, she makes it public. Then she computes phi of n, which is just p minus 1 times q minus 1, which will be secret. Then she chooses some integer e, co-prime to phi of n, such that the inverse of e mod phi of n exists. So this e will be public. Then Alice computes the inverse of e mod phi of n, which she calls d, and this d will be the secret of Alice. So in short, n and e are public, p, q, and d are secret. At the same time, Alice announces that each message m can be transformed in some manner as an element of z over nz. So this is not a problem. This will be public. Anyone knows how to translate a message m into an element of z over nz. Now, Bob wants to encrypt a message m. So m now is an element of z over nz. Bob wants to encrypt this message M using the public key and E of Alice. He does the following computation. He puts M to the power of E modulo N. We call this C as the ciphertext. So this will be the ciphertext. And Bob sends this ciphertext to Alice. So Alice has to decrypt this ciphertext and get back the plain text M. She does the following thing. She takes C, puts it to the power of D, which is her secret, modulo N, and this way she gets back M. And why it works? Because C to the power of D is equal, C itself was just M to the power of E. So this here is M to the E to the power of D. It's equal to M to the power of ED, and E and D are inverse of each other modulo phi of N. So E times D is a multiple of phi of N plus 1. You can write this as M to the phi of N to the K times M, coming from here. And as I explained the general fact coming from group theory, M to the power of phi of M, phi of N, M to the power of phi of N here is just the identity element 1. So we are left just with this M, which was the plain text of the beginning. So that's why RSA works. Now I give a toy example of this RSA to understand why and how it works. So you may take P equal to 5, Q equal to 11. These are kept secret. N 5 times 11, 55, which is public. Phi of N is just 5 minus 1 times 11 minus 1, which is 40. It's secret. We may take E to be equal to 3. 3 is co-prime to 40, so it's okay. E is public. We compute the inverse of this E modulo 40 by the extended Euclidean algorithm. And this inverse is 27. So D is 27, which is secret. We may take the alphabet A to Z as to be identified with 0, 1 to 25. Pay attention that here 0, 1 to 25, we are taking these numbers in Z over 55Z. So modulo 55. Okay. To encrypt the letter E, which is 4 modulo 55, Bob computes the following thing: 4 to the power of 3, which was E here. 4 to the power of 3 mod 55, giving just 9. And Bob sends this number 9 to Alice. To decrypt this message, Alice does the following. So 9 to the power of the secret D, which is 27 in this case, modulo 55, which gives back 4, and the letter E. Why this works? The same thing as I explained before, because 9 to the power of 27, 9 itself was 4 to the power of 3. So all of this is just 4 to the power of 81. 81, if you divide this 41 by phi of 55, which was 40, it gives you 2 times 40 plus 1. So you write this as 4 to the 40 to the 2 power times 4, modulo 55. Now 4 to the power of 40, as I explained, is just 1, and all remains is this 4 here, and we get back the plain text which was 4. Now I want to explain that Alice can sign even messages with her RSA system. So if Alice has an RSA system, with this system she can sign messages. How can she do this? So to sign a message M, which is just a number in Z over NZ, she does the following. She takes the message M to the secret that she knows, which is D, M to the D modulo N, and then sends it to Bob. So Bob wants to verify if this signature or this message which is signed comes from Alice or not. So to verify this, Bob takes the public key of Alice, which is E, and computes the following thing. He received M to the D, so Bob takes M to the D, put it to the power of E, which is publicly known, and as I explained before, this gives M to ED, and M to ED is just congruent to M mod N. So if the result of this computation is M, Bob accepts the signature and the message as coming from Alice, because no one than Alice knows the secret D. But if the result of this computation is different from M, Bob rejects the signature, and he knows that the message is not coming from Alice. So that's how we can use RSA to sign messages. As a last word, I want just to say that Alice even can use her RSA crypto system to share a secret key for doing symmetric cryptography with Bob. I mentioned a few slides before that one of the problems of symmetric cryptography was that before Alice and Bob start exchanging messages or something, they have to share a secret key to use for their symmetric cryptography. Now, I'm saying that Alice can use her RSA crypto system to send a secret key for symmetric cryptography with Bob. So all Alice has to do is the following. Say M is the key that she wants to share with Bob. M is a number, as you saw earlier. In the case of Caesar, M was 3. In the case of a matrix, it was a matrix. So you may think that M is somehow a number in Z over NZ. So all Alice has to do, she computes M to the D mod N and sends it to Bob. And Bob does the following thing: M to the D 2E mod N, and Bob this way can find M. as I explained, this is equal to n. So you see that we can use even RSA to share a secret key for symmetric cryptography. So this is not the end of the story, but in this talk, that is all I can say about cryptography. I hope that you enjoyed this talk, and so thank you for listening to this talk.